Alright, next topic on the plate is triple integrals. So first, I'll discuss just regular triple integrals in Cartesian coordinates. So if the boundaries are already given as constants, then we essentially just have a cubic shaped volume of integration, kind of how we had a rectangular area of integration for the iterated or rectangular double integrals. So it's basically just a simple matter of doing the calculation. So if the region is being described in the problem, it's a good idea to go ahead and draw the region to visualize what the bounds should be, and you may find that the boundaries are still described well enough by constants, or they may need variables. But just remember to put the variable boundaries as the innermost. So in other words, if you have y in terms of some function of z, then you need to have dy as the innermost, or first variable that you integrate with respect to. So that way we have more z variables that replace y during that integration, which we were about to integrate z variables anyway, so it doesn't matter that we add more z variables. But you don't want to be adding z's into the equation after we've already integrated with respect to z, because then you're going to have variables in your final answer. You don't want that. Alright, so the next type of triple integral would be those in cylindrical coordinates. So without going into the derivation or the background of the change of variables formula for 3 dimensions, let's just get into the formula, and we'll say that the change of variables formula specifically for converting Cartesian into cylindrical is that dv, which that is to say dx, dy, dz, is transformed into r dz, dr, d theta. And the formulas for converting the integrand variables are that x becomes r cosine theta and y becomes r sine theta, same as in 2 dimensions, and then z does not change. So overall it's pretty similar to a polar coordinate conversion. So the first step to do this is draw the shape and the boundaries, then determine what the integral boundaries are going to be, and then start evaluating the integral and changing the variables to the new ones, via those equivalencies. Alright, so the final type of triple integral is going to be those in spherical coordinates. So this is going to be a little different, a little bit more complicated. You're going to have to invoke a new variable called phi, which is basically just like an angle that tells you how far up or down the z-axis you are. So it's just kind of like the latitudes on Earth, and just like the latitudes on the Earth, it's only going to range from, it's only going to have like a 180 degree range. So it's going to go from basically negative pi over 2 up to positive pi over 2. So we also continue to use theta for the spherical coordinates, which, since we're on this topic, is like, it's kind of like the longitude. So it goes all the way around the Earth, unlike the latitude. So it's going to have a 360 degree range. So it's going to go from 0 to 2 pi. And we have a rho for the radius instead of r, but it's essentially the same thing. We're just kind of making that distinction because rho is not constrained to a plane like r is, but still basically the same concept. Pretty intuitive. So the way that this is calculated is similar to the cylindrical coordinates. We're going to have this formula to replace the dv, in other words, to replace the dx, dy, dz, and that formula is rho squared times sine of phi times the partial of rho times the partial of theta times partial of phi. So then the formulas for the variables are as follows. X becomes rho sine phi cosine theta, y becomes rho sine phi sine theta, z becomes rho cosine phi, and then rho is just calculated from the Pythagorean theorem, which is that it's going to be x squared plus y squared plus z squared equals rho squared, and then just take square root of the other side.